A steam condenser has a separate air. A steam condenser has a separate air and condensate pump. This side we are air pump, and this side we are condensate pump. The air, the entry of air is pump is screen off. The steam enters the condenser at 38 degrees Celsius. T1 is 38. Air is removed at 36 degrees Celsius. The quantity of air filtration from the various sources that is coming into the condenser is 5 kg per hour. We want to find out the volume of air handled by the air pump at this section 3, and we want to compare this quantity with that have to be dealt by using a combined air condensate pump. That is, if there is no section and we use this pump to this side, then how much is the amount of the capacity of that pump. So T1 at section 1, T1 equal to 38, at section 3 T3 equal to 36, at T2 equal to 38. Mass of air leak is 5 kg per hour, and he says that neglect the pressure of air due to at the entry of the steam, so we assume PA1 equals to 0. Since the inlet initial pressure of partial pressure of air is 0, so whatever the P mix is due to the steam pressure only. At condition 1, temperature is 38, so from steam table we can find out Psat value, which is 0.06624 bar. We'll apply the now Dalton's law of partial pressure, which says that the total pressure is equals to sum of individual pressures. So condenser pressure is equal to P mix is equal to partial pressure of steam at section 1 plus partial pressure of steam at section 1, that is equal to 0.06624. Partial pressure of air is given as 0, so the total value remains 0.06624 bar. Same Dalton's law of partial pressure we can apply at section 3. At section 3, first of all, we'll find out the saturation pressure of the steam at section 3. So PS3 is equal to Psat at temperature T3. Temperature T3 is 36. So from steam table, PS3 will come out to be 0.05940 bar. Again, we'll apply the Dalton's law at section 3. We have PS3 plus PA3 P mix. Condenser pressure throughout remains constant. So we'll substitute the same value of P mix, that is equal to 0.06624. PS3 is equal to 0.5940. So partial pressure of air at section 3 is equals to 0.00684 bar. Once we know the partial pressure, we can apply the ideal gas equation to find out the specific volume of air at section 3. So V3 is equal to RT3 divided by PA3. R is 27, temperature at 3 in Kelvin is 36 plus 273, and partial pressure is 0.00684 10 to the power 5. So specific volume at section 3 is 129.6 meter cube per 8 kg. Since the volumetric flow rate of air is 5 kg, the mass product of air is 5 kg per hour, we can very well convert mass product into volumetric flow rate by multiplying mass product with the specific volume at section 3. So volumetric flow rate of air, or it can also say that the capacity of air pump is the product of mass of air multiplied by specific volume, 5 multiplied by 129.6. So flow rate will be equal to 648.1 meter cube per hour. If we assume that there is no cooling section, then we have only one inlet and outlet, both temperatures are 38. But in that case, the volumetric flow rate, in that case the P mix is equals to 0.66024, but this pressure and this pressure is same. So the total value of partial pressure will come out to be 0. Let's check it. So P mix is same, PS2 is same as Psat is 0.66024. So P mix is PS2 plus PA2. P mix is same as 0.0662. It means there is no contribution of air. So this cannot be assumed like this, because this temperature must be lower than this, then only the partial pressure of air can be handled. So in numerically the 38 is not possible. So volume of air cannot be calculated because data is not sufficient for us.